So our next speaker is Professor Andrea Goldsmith from Stanford.
Thank you. Thanks. It's really a pleasure to be here to celebrate Jean's retirement. And so my story goes back to my alma mater, Berkeley. So I want to tell a little bit about how Jean and I met and got connected. I'm surprised you let me up here to do this, but here we go. All right, so Jean and I came to Berkeley around the same time. He came as a professor in 1981, and I came as an undergraduate in 1982. But I was not that interested in networks, so I didn't actually take any classes from Jean when I was an undergraduate. And we didn't meet until I came back to Berkeley in 1989 and joined Praveen's research group. And there's a few people in this picture that may, oh, sorry. Okay. A few people in this picture that may still be in this room. So this was all of us, slightly younger in 1989 in Praveen's group. Now I see there's a lot of people here that got their degrees from Berkeley, but not everyone. So just so you know what happens when you get a PhD at Berkeley, this is the trajectory. So you start out, there's a PhD preliminary examination, then there's a qualifying examination, then you write your thesis and hopefully it's signed off on, and then you get your degree. So Jean was part of all of these blocking points in my trajectory here. So now remember, I wasn't working on networks. I was working on communications at the physical layer. So prelim exam went fine. He gave me a kind of cool Markov problem, as I recall, and he must have liked my answer because he passed me. So I was done with prelims. And then we come to the PhD qualifying exam. So this is where you present kind of where you are in your research, and if you pass that, then you get to go off and write your thesis. So picture the day and time and place. This is from my qualifying exam. It was April 9th, 1992, 10 a.m. in the Hughes room, which still exists. It has not been torn down to make room for something else in Corey Hall. And my topic was what I'd been working on, the Shannon Capacity of time-varying channels. And my thesis, or the committee, was Jean and Praveen and Jim Pittman, who was one of my favorite professors of probability. And so I launch into my talk, and first couple slides go fine. And then I'm getting a little confident, kind of getting on a roll, and then comes slide 5. I went back and looked, slide 5. So here, I'm talking about the continuous time channel capacity, where you kind of decompose the channel using Carhoon and Loew decomposition. And then Jean asks, what does this have to do with Hilbert spaces? OK, well, the correct answer at that time for me was, I don't know what a Hilbert space is. I don't remember. I took real analysis as an undergraduate. And so here, David Hilbert raises his head in my exam. And of course, I have no idea how to answer this question. And so my vision of getting a PhD and going on and becoming a professor is vanishing at a very rapid rate. It didn't come to me a Hilbert space, just for those of you that don't remember. It's a special case of a vector space. It has a norm, and it's complete, so all limits of limits are in the space and all that. But I didn't remember any of this. Now, if at the time I was as skilled at deflecting questions that I don't have the answer to, I would have said nothing, can we move on, right? Because that's a reasonable answer to pretty much any question, especially if you don't know the answer. But of course, I was not skilled in deflecting questions or being an arrogant academic and saying something like that in a thesis defense. So I kind of stuttered and got a little choked up, thinking that my degree was going out the window and all this. Somehow, I did manage to get through the exam, and I passed. So then I was moving on to the thesis writing, and Jean signed off on my thesis too, so did Praveen. And so there I was as a graduate, got my PhD. And what I realized at that point is that made me Jean's academic sibling, because he got his PhD from Praveen a few years before I did. And so all of these tough questions were really just to make sure of the purity of the lineage, so that Praveen's group was not demeaned in any way by me getting my PhD. So then I graduated and moved on. And then it turned out, even though Jean had been working in networking and I'd been working in wireless, we started actually coming closer together in terms of our research, partly because of the PATH program. So the PATH program funded my research. This was a program to create automated, basically autonomous vehicles on highways in California. This goes all the way back to the early 1990s. And Jean was working on the communication architecture, and I was looking at the wireless piece of this. And so then I was honored to get asked by Praveen and Jean to write a chapter on wireless communication in the second edition of their book. And so I guess I somehow convinced Jean that I knew something about wireless enough to put this in that chapter. And then even recently at a comm theory workshop, there was a session on wireless networks, and lo and behold, Jean was one of the speakers. So of course I took the opportunity in the middle of his talk to ask him about Hilbert spaces. And to remind everyone that payback is hell when you give someone a hard time on an exam. So anyway, Jean, it's really been an inspiration to know you as a researcher. I don't appreciate everything you've done in networking because I don't work in that field, but I know some of it, and it's been a wonderful journey to watch your all of the things you've done. You're a great professor. I took, believe it or not, information theory from Jean right at the very end of my time at Berkeley. I think I got an A- because I was not nearly as good in some of the math, and it was, but that was the first time information theory was offered at Berkeley in the whole time that I'd been a student here. So it was fun to learn it from you from a different perspective, and also you've been a wonderful friend all these years. So anyway, with that, I'm going to launch into talking about this wireless connection and what's next for wireless networks. Note that John's talk was about 4G networks. Well, we're moving on to 5G. So I'm going to talk about what's new and exciting in the next generation of wireless networks. So as you've seen, I've been working in wireless my whole career, 30 years. And to me, it's a really exciting time to be in wireless, maybe the most exciting time, because in the past, working in wireless was really about either people talking to other people over wireless connections or accessing information over the internet. And now we have so many more ways that we want to use wireless, whether it's in sensor networks or in devices inside our bodies, all this automation of highways, of smart cities, of the energy grid. And so there's a lot of interesting new applications which require us to build different types of networks than we've had in the past. One of the big challenges is the fact that there's very limited spectrum. So this is a graph from a couple years ago which said that as of 2013, the licensed spectrum, which is what the cellular phones use, is 300, or is full. And of course, we've gone on since 2013 to build more and more wireless devices and use more and more spectrum. But we're not using it in the licensed band. We're using it over Wi-Fi. On the horizon is millimeter wave, where there's tens of gigahertz of spectrum. And one of the new things that I'm working on is molecular communication. So why not try to use molecules to send information? So I'm going to talk about that a little bit at the end. So if the license bands are full now, how are we going to support the Internet of Things? So the notion of the Internet of Things is that every single device with an on-off switch is going to be able to connect to each other and connect to the backbone internet. And that's a very different type of network than we've built up until now. In particular because these devices, so maybe in my tennis shoes or in my sensor in my backyard or in my thermostat, these are devices that have very low energy sources, and they may actually not even have a battery, and also low data rates. So up until now, we've been pushing for higher and higher data rates, and now we're going to devices that maybe need bits per second. The interesting thing to me about the Internet of Things is that it's not so much that it's important that my tennis shoes talk to Jean's tennis shoes, or I guess not tennis shoes. What's important is that collecting all this data and sending it up into the cloud is where, and doing the processing in the cloud and figuring out how to utilize all this data, that's where the value of the Internet of Things is. And so that means we need a communication infrastructure that can do all this for devices that, again, have very limited energy and maybe need to last the lifetime of a building or of a car or of a bridge and so forth. So, so how are we going to build networks like this? One of the questions that I ask, because I still work in Shannon Capacity, is are we at the Shannon Capacity limit of wireless systems? So I'll just take a show of hands. How many people think we're at the Shannon Capacity limit of wireless systems? Raise your hand. How many people think we're not? Okay, so you're all wrong because we don't know the Shannon capacity of most wireless channels. And that actually goes back to my PhD research. We were looking then at how to compute the Shannon capacity of wireless channels, and it's a hard problem in most cases. So if we don't have a model, which is the true for millimeter wave channels, we don't have good models for that, certainly not for terahertz, not for molecular channels. If we don't have a channel model, you can't compute Shannon capacity. If the channel's time varying, even though I got results for that in my thesis in some special cases, for most time varying channels, we don't know the capacity. We don't know the capacity with interference or relays. That's been an open problem basically since the beginning of Shannon theory. Cellular systems have interference, and so they introduce interference, so we don't know capacity of those systems. Don't know capacity of multi-hop networks. And as soon as we introduce things like delay or energy or dollar constraints, you can't drive the probability of error to zero, which is the underlying premise of Shannon capacity. So we can't bring in things like hardware constraints or limited energy into solving Shannon capacity. So I'd say, well, then why do we work in Shannon capacity if it doesn't tell us anything interesting about designing these systems? In fact, that's not true. So Shannon capacity does provide, in my experience, a lot of interesting insights into the design of wireless systems, as well as performance upper bounds. So I'm going to talk a little bit about some of the enablers for this next generation of networks, including utilizing millimeter wave spectrum along with massive MIMO, rethinking cellular system design completely through a notion called software-defined wireless networking, a little bit about new physical layer and multiple access techniques, and then green networks. Now, you might say, well, why am I talking about new physical layer design? Physical layer's been dead multiple times. So it was first declared dead in 1971 when they said coding was dead. Then in the 80s, it was dead. In 2014, it was also dead. But there actually is some life in new physical layer techniques, which I'll talk about briefly. OK, so what's up with millimeter wave? There's tens of gigahertz of spectrum up there. So every single commercial system today fits into the millimeter wave bands, which is why people are starting to look at it. The problem is that when you go to these very high frequencies, path loss is proportional to 1 over lambda squared, so you get very high path loss. It's very difficult to communicate at large distances if you're just sending things through an omnidirectional antenna. So what you do is you build these large antenna arrays, which can point a very pencil-thin beam at any particular receiver, and therefore you don't have that same kind of path loss, and you can get a strong signal at the receiver. In addition, once you form these kind of pencil-thin rays, everything that we've worked on for decades in terms of enabling wireless communications goes away. So there's no interference because that beam is not causing interference to any of the other radios. There's no multipath fading because there's no reflections that arrive at the receiver delayed in time and phase and cause the random changes in the received signal strength. And there's very little attenuation because, again, you're channeling all of your energy in exactly the direction that you want to go. So you might say, well, great, this solves all of our problems. We don't need to do any more communication theory. And the other nice thing is you say, well, but that's a very big array. However, when we go to millimeter waves, the antenna elements are small. So you can build these arrays, and they're not so big. So I like to call this millimeter wave massive MIMO the dynamic duo of 5G communication, because they kind of compensate for each other's strengths and weaknesses. And so there's a lot of excitement about building these massive MIMO systems for millimeter waves. The problem is that in order to form this very fine beam, you need to know the channel perfectly. between every transmit antenna and every receive antenna. And that's very hard to do. And in addition, if you put an object in between the antenna array and the receiver, this whole nice, beautiful pencil-thin beam goes away and it gets scattered. And so all of these benefits go away. So it isn't the panacea that we would like for 5G communications, but it's certainly a piece of what's going to be in this next generation of systems. Okay, so rethinking cellular system design. Here's another question. When was the paper that laid out how cellular system designs are architected, or how cellular systems are architected, written? Which decade? So first cellular system was deployed in the 1980s, so it was before that. So how many people think it was the 1970s? Raise your hand. That's when John came to Berkeley. Okay, how many people think it was the 1960s? 1950s? 1940s? It was the 40s. It was a paper by D.H. Ring from AT&T Bell Labs that laid out, if you read that paper, basically lays out exactly the architecture of cellular systems. You have a base station in the middle of a cell that talks to all the users in the cell. You do handoff. This is all written in a 1948 paper. And we still design systems the exact same way. Okay, of course, we've advanced what we do at the physical layer. We're no longer using analog, we're using digital and all these sophisticated techniques. But the basic architecture of cellular systems have not changed, even though we've incorporated all these techniques. So you can think about new ways to design cellular systems where you can have the base stations cooperate. That was incorporated in the 3GPP standard. You can have relays. You can have a mix of small and large cells. You can distribute your antennas throughout a cell. These are all things that have been incorporated into research and also some experimental systems. But we've never gone back and said, well, maybe we should rethink the whole architecture. And if we did that, then we might be able to get big gains, either in capacity over what we have now, or perhaps in other metrics like coverage. I live off Sand Hill Road, most expensive real estate, probably in the world. And every time I drive up to 280, my cell phone call gets dropped. I mean, this is a voice call. This is not a high-capacity call. So we still don't get good coverage, and that's going to be a real problem if we're using these networks to do autonomous driving. And then the energy constraints that the Internet of Things introduce. If we're going to start worrying about supporting devices that are running off small batteries or collecting energy from the sun or from vibrations, we need to focus more on the energy consumption of the network than on the data rates that we're going to get. So small cells is something that certainly gives us a boost in capacity. And the reason is that if you build an architecture so that every cell can support, say, 100 users, and then you shrink the size of the cell and you still support the same 100 users, overall your system capacity grows exponentially. So it's been known for quite a long time that going to smaller cells gives us higher capacity. The problem is, how do you optimize all these small cells? And this gets into doing optimization in the cloud to manage the parameters and the resource allocation of the different users. And so this is a notion called SON, self-organizing networks, where you just send the parameters of the network up into the cloud and you do some kind of optimization and then send back the parameters. So if you do that for cellular, you could do that for all networks. You could do that for Wi-Fi, you could do that for millimeter waves, vehicular networks, and so forth. And this kind of gives rise to this notion of software-defined wireless networks. So Nick McEwen, who did the OpenFlow, we were graduate students together. In fact, the very first probability class I ever took as a graduate student was with Nick. So he's coined the notion of software-defined networks for wired networks. Wireless, it's a little bit different, because here you've got a different set of resources to allocate, and the way you allocate the resources impacts the different networks. So for example, if Wi-Fi and cellular are sharing spectrum, as is the case now with unlicensed LTE, you want to manage that spectrum between the two different networks. So if you talk about how do you do frequency allocation, this unified control plane can allocate frequencies across the different networks. It can allocate different power. It can decide which network a particular application should go over. So if I have a video, say an HD video, I want to go over a millimeter wave network because it has the highest bandwidth. But when I move away from that network, I need to do a seamless handoff to another network. So this is the notion of the software-defined network architecture. And in fact, if you want to go to the Shangri-La of what this means, you say, well, I don't need any systems at all. I'm just going to have a bunch of distributed antennas at different frequencies and let the unified control plane figure out exactly how to utilize these antennas for the different systems. Of course, there's a lot of challenges in doing this. The algorithmic complexity is one. As someone who worked on frequency allocation in second-generation networks, that was a NP-hard problem. It's a graph coloring problem. And now things are even harder because we have multiple antennas and power control and small and large cells and so forth. So I call this an NP really hard problem. It's not just NP hard. But fortunately, thanks to many people here and colleagues elsewhere, there's a lot of advanced optimization tools to solve these optimization problems. But one of the things that's kind of unique to wireless is that we don't need to look at this just in terms of distributed optimization or centralized optimization. So if you can't get all the information to the cloud because of the latency or the complexity of doing things in the cloud, you could do things fully distributed, and that's how Wi-Fi works. Generally, your Wi-Fi access point is doing optimization fully distributed. But there's this notion of fog optimization where now you can kind of form these small neighborhoods where you do centralized optimization within a neighborhood, and you can scale the size of the neighborhood such that if it's very small, it's fully distributed optimization. If it's very large, then it's fully centralized optimization. And you can look at how the performance changes with the scaling of the size of the network. And this is something that I think is, or size of the neighborhood. I think it's something that's really important for wireless network optimization. We have some work on it, but I'm not aware, and maybe people are, have seen it in other contexts, of a real theory behind looking at this fog optimization and how much can be gained over distributed and how much is lost versus centralized. Okay, a couple other things I just want to mention. So in fact, there are new physical layer techniques in terms of waveforms for 5G that are robust to changing channels, that are more bandwidth and energy efficient. And then with the Internet of Things, we need new ways of doing multiple access because chopping things up in an orthogonal manner is not efficient when you have these very small devices. So there's kind of a whole new set of access techniques that we can take a look at. And one of the other things that we're doing in my group now is machine learning. Now, I'm not, people that know me, I'm not a big bandwagon person. Like if everybody's working in machine learning, I'm going to run the other direction typically. But it turns out that machine learning is very useful in certain aspects of communications, particularly when you don't have a channel model. So when does machine learning work well? It works well when you don't have models. In most communication system designs, we have good models. For most wireless networks, we have good models for the channel. But as we move to things like millimeter wave and terahertz and molecular, there are no good models. And it turns out that we first applied this to a molecular communication system we're working on, because there was no alternative when you don't have a channel model, and we got a 10x gain in data rate by using this for our detector to remove the intersymbol interference. So we've been doing some other work on applying machine learning in contexts where either you don't have good channel models or network models, or you have good models but you don't know the parameters. It's too expensive to learn the parameters. So I think that's an interesting new area to look at. And so that brings me to the chemical communication. So the way I got into chemical communication is I had a postdoc, a graduate student from York University who had built a chemical communication system there. It's an on-off keying system. So you're basically now embedding bits in chemicals instead of electromagnetic signals. So the system that he built was an on-off keying system with vodka. Okay, so 1, send vodka. 0, don't send vodka. And there's a breathalyzer on the other end. And the problem with the breathalyzer is that just like we're going to do tonight to celebrate Sean's retirement, you get saturated eventually. I don't know if it'll be with vodka, but eventually the sensor gets saturated and you can't communicate anymore. So, so he came to my group and we started working. I thought this was a pretty cool thing to look at because it's completely green field. Okay, the way that signals propagate as chemicals is through diffusion. So it's not Maxwell's equations, it's diffusion equations. So we don't have good channel models. And everything about designing the system is new. How do you modulate bits? How do you send them through the channel? How do you mitigate the impairments of the channel? How do you have multiple users sharing this channel? How do you do networking? This is all completely new, as are the fundamental capacity limits. So it's a very fun area to work on. And we actually have a system in our lab right now. So because the vodka was not very efficient and only got about a half a bit per second, which you might say, well, that's ridiculous. But actually, if you think about using this for in-body communication to turn on artificial organs or to do drug delivery adjustments, half a bit per second isn't bad. We got up to an order of magnitude above that using 2 chemicals. So now we use an acid and a base. Windex and vinegar, basically. And so Stanford Report did an article about sending text messages using Windex and vinegar, but of course, saying the undergraduates probably wouldn't. Vodka's more fun, yes, but how do you cancel out the alcohol is the problem. Bloody Marys don't work as far as I know. So anyway, so we applied machine learning to equalize the tail of the system response, which again, this is through diffusion, so it takes a long time for the chemicals to diffuse. And so we're continuing to work on this. It's a lot of fun. And the last thing I'll talk about before wrapping up is some new work that I started as part of the NSF Center for Science of Information. Kumar's part of that as well, where we wanted to take our ideas of communications and information theory and apply them beyond communication systems. So I was thinking about, well, what looks like a network outside of traditional communication systems? So I thought, well, the brain looks like a network. I was naive because I thought it was a wireless network, and then it turns out that the way these signals propagate through the brain are through these neuronal chains, which are actually wired, not wireless. And so we looked at a bunch of different things to try to understand where we could apply our techniques to neuroscience. And what we came up with in the end was looking at epileptic seizures to try to find the focal point of an epileptic seizure. So for patients with epilepsy that's drug resistant, the only way to stop the seizures is to cut out the part of the brain where the seizure starts. So you get one neuron that starts oscillating very quickly. That spreads to surrounding neurons because they're all connected, and eventually the oscillations spread enough so that you have a seizure. So if you can go back and find that seizure onset zone, you can give the doctors better information about where they should be cutting. Because the way they do it now is the doctors will implant this sensor. They'll take a look at this grid and say, oh, I think this is where, this sensor is where the seizure onset zone is. So we introduced an algorithm based on directed mutual information that's basically reverse engineering. So it's looking at these sensor data and reverse engineering through causality back to where the signal started, where the seizure started, the seizure onset zone. And it turns out we've run this on about 20 different data sets, and our algorithm beats the doctors. What I mean by that is that the data sets, they annotate where the doctor identified the seizure onset zone. Our algorithm gives a smaller zone, and it matches the doctors in every case. Now, we haven't gone back and looked at what we're trying to do now is say, well, if our algorithm did not match the doctor and they did the operation, was it successful or was it not successful? Because that would give us more information about whether, when we don't agree with the doctors, if we're more accurate or less accurate. So let me wrap up. 5G networks, a lot of fun. I hope you're not going to stop working in wireless because we could use your insight and ideas. There's not only going to higher data rates for better cell phone usage, but also for all these Internet of Things devices. I think the notion of this cloud-based software to manage wireless and how we can do that optimally through, this fog optimization is very interesting. At the physical layer, using small cells and massive MIMO, there's a lot of research to be done there as well. And then looking at energy efficient design. So let me just say last, Jean, can't believe you're retiring. It makes me feel really old. But best wishes on your retirement. Thank you for your incredible contributions to networking and to wireless, to my alma mater, Berkeley, and for your inspiration and your friendship. And then this last quote, happiest person is the person who thinks the most interesting thoughts, and we grow happier as we grow older. So I hope that applies to you throughout your retirement. Thank you.
So maybe time for a couple of questions before we head off to the break.
Hilbert spaces.
That's my question is, what does this have to do with it?
Nothing. Can we move on? See,
Any other questions?
yeah.
I think Jean's question actually is related to the question I was thinking, struck by, right? Which is, no, seriously, right? Is a lot of this, right, seems to be involving managing the next level of complexity, right? Beyond the things that we had been able to do before, right? And we think about, like, let's think about the Hilbert space, right? It's like, let's look at the simplest thing. And do you see, what do you see as the role of this sort of, let's look at the simple thing view in this modern kind of space that you've laid out?
Yeah, it's a very wonderfully insightful comment in the following sense, and let me go back to this picture. Because I think in some ways there is an analogy here where this is kind of a very general network, and then you go to this, which is very simple, right? I mean, it's just you've got a bunch of antennas out there, and it removes the auspices of any particular set of constraints, like in a Hilbert space, where you've got, it's a generalization of Euclidean space. So, and the problem with this is that by removing levels of or making the problem simpler here, because now I have no Wi-Fi or cellular, I just have a bunch of antennas, it makes the problem harder, right? Because without those constraints, now we have to think about, certainly this optimization becomes a lot harder. And so in some ways, the reason we, as engineers, design systems in layers or as particular sets of protocols is because it reduces the design space down to something that we can get our hands around. When we do that, we throw out optimality. It's always better, if you have something more general. So I think, to go back to the spirit of your question, what I see for the next wave of wireless and networking research in general is, and we see this happening with software-defined networks and OpenFlow and the work that Barefoot Networks is doing, is can we throw off these constraints that we've put on ourselves as engineers, because now we've had decades of evolution of technology and understanding about optimization, and go back to these problems and say, let's rethink them with all that knowledge. And maybe that will lead to a better solution, or maybe it will just make us very frustrated because we won't come up with answers. But I think it's a very worthwhile endeavor.
Great, thank you, Andrea.